Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for Calculus 2 students or integral calculus students who are just learning how to do integrations of trig functions using U substitution and fun stuff like that. Now, if you're one of my students, you probably have already seen this style of problem. However, I never really covered it in a classroom environment, so I think it's probably a good idea to spend a little bit of time talking about it here. We're asked to evaluate the indefinite integral of cosine squared of x dx. Now again, if you're one of my students, you know that I kind of talk about the ultimate goal when dealing with trig functions or products of trig functions as integrands is to get them to have even powers, if possible. And I should say that's actually not always the case, but if you have an integral involving some trig function, I'll call it sub 1, times another trig function, sub 2, our normal goal is, if given an integral of the product of two trig functions, we would like to, if at all possible, get one of them through a U substitution to have an even power. But that's actually a secondary goal. In reality, your first priority is to see if you know the antiderivative of this product. This actually ends up happening a lot, and people don't pay attention to that simple step. They just run right through and try to do U substitutions. A perfect example of this is something like, the integral of secant of x times tangent of x. A lot of people will start changing things to sines and cosines and stuff like that to see if they can integrate this. The reality is the antiderivative of secant tangent is the secant itself, because the derivative of the secant is the secant tangent. So this is something to pay attention to. Don't just run into U substitutions or trying to manipulate powers or trying to use trig identities. If you have an integrand that is easily integratable, that is the derivative of a very common trig function, for example. The second thing you should always do is look for obvious trig identities. And this again is something that people often gloss over. I know when facing the tangent squared of x dx, that can be somewhat of an intimidating integral if you're not used to integration. However, think about a trig identity that will make this a lot easier. The Pythagorean identity that we have is 1 plus tan squared of x is equal to secant squared of x. That is, tan squared is equal to secant squared minus 1. Once you get down to that, you could break up this integral into the sum, or difference in this case, of two sub-integrals. And by the way, that integral dx just means integral of 1 dx. The antiderivative of secant squared is tangent, and the antiderivative of 1 is just x. And you get down to this beautiful answer right here. Another example of keeping an eye out for obvious trig identities is if you are asked to integrate sine of x times cosine of x. A lot of people will do a U substitution on this. There's nothing wrong with doing a U sub here. However, if you're pretty ingenious, you can just do this. Multiply top and bottom by 2. So you have 2 sine of x cosine of x dx. Bring the 2 in the numerator into the integral, and then recognize that's a trig identity. That's a sine of the double angle. The antiderivative of the sine would be the negative cosine of whatever the argument is, but because the argument is being multiplied by 2, you are going to multiply its antiderivative by the reciprocal, or in other words, 1/2. And of course, that can be cleaned up pretty quickly. So just pay close attention to those two first steps. Always check to see if you can just directly integrate. If that's not possible, look for obvious trig identities. If both of those tactics fail, then you have to get fancy. So the thing I do is I start looking for u-subs that will force even powers. Now this is a rule of thumb. There are always exceptions to rules of thumb. The exceptions would be like if all the powers are already even, then you're out of luck. Or another exception would be if you're dealing with secants and tangents. So there are exceptions to these rules, and you can't memorize, well, I suppose you could, but I don't recommend memorizing all of these exceptions. Instead, just start practicing the problems and start really developing a natural intuition to what you should do with these problems. If you look at our original question here, which was a while ago that we started this, that's the integral of cosine squared of x dx. It's already an even power, so a u-sub is not going to be useful here. And that gets us to yet another normal goal. If all the powers involved in the integral are even, and by the way, you're only dealing with sines and or cosines, then you have to switch to using half-angle identities to reduce those powers. By the way, some people call those the power reduction formulas, which is perfectly fine. I just learned them when I was a student as the half-angle identities. A rose by any other name is still but a rose. And that's what we're going to use here, the half-angle identities. And you should recall that the half-angle identity for the cosine is the following. But in this case, we're not dealing with the cosine of x over 2, we're dealing with the cosine squared of x. So you can modify this and double up this angle. If you double up that one, obviously, then the argument of the cosine inside the square root will also double. And if you square both sides of this, the square root disappears. And that's what I'm going to replace the cosine squared of x with. From this point forward, the rest of the integral is not so bad. The antiderivative of 1 is, well, x. The antiderivative of a cosine normally would be a positive sine of the angle. But because the angle itself is being multiplied by 2, you're going to divide the antiderivative by 2. That's just offsetting the multiplication of the argument by 2. And because we have finished an integral, an indefinite integral, there's that required constant of integration. You're more than welcome to distribute that 1/2 through if you want, or you could leave it factored out. It actually does not matter. Now, I did use this video to really reinforce some ideas when working with trig or integrals that involve trig functions, and I think that's something to always go back to. Just remember, start with simplicity. Right? Look at what you're integrating, ask yourself, do I know the antiderivative? If you don't, then move on to more complex statements like, is there a trig identity? In this case, there is, but the only trig identity that we'd be using, other than the one we actually did, would be the Pythagorean identity, but integrating this is just as bad as integrating the cosine squared, so I'm not going to try that. But there was another identity. That identity actually was the power reduction formula or the half-angle identity. So technically, I could have lumped this statement in with 2, that I'm actually looking for an obvious trig identity. Well, the obvious one is the half-angle identity, so that's a good one to use. If none of that works, look for u-subs that will force even powers. But just remember, if all the powers are already even, you're out of luck. Go ahead and just do power reduction formulas. Now, everything I've said in this video pretty much only pertains to products involving sines and cosines. With secants and tangents and cosecants and cotangents, there are modifications to this list. Not actually too much in the way of modifications. Probably the one thing that's useful to know there is that you have more options, because the derivatives of, for example, the secant or the cosecant steal away powers of both the secant and the tangent, or the cosecant and the cotangent, and that ends up giving you a lot more flexibility in evaluating an integral involving those styles of functions. Anyway, that's it for this video. I'll see you in the next one.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Names for what they are and work together until you feel at peace. Says, listen close, don't talk too much, that is isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.